Let's see. All right. So if you're watching this on YouTube, just for the record, we've been forced into Science Hall 200, so we don't have all the gadgets around us. Anyways, yeah. So last time we were talking about the Dirac equation. All right, and I think we derived it. So we talked about where it comes from, and we wrote it in terms of the Dirac gamma matrices. Right, and these gamma matrices are basically, they're just a shorthand notation for the alphas and the betas, but they satisfy the same anti-commutation relations that the alphas and betas did. So this is 2G, right? And they all satisfy, well, the gamma 0 squared satisfies this, and the gamma i's squared satisfy the minus ID. Okay, and we introduced the Feynman slash notation, which said that if you have gamma mu being retracted onto some vector, you could write this in shorthand notation as A slash, right? And so that allowed us to rewrite our Dirac equation as I del slash minus M psi. All right, and you can easily show using the anti-commutator relation that if you take A slash times A slash, it's the same thing as the 4 vector A squared. Okay. All right. So to make any progress, we had to choose a particular representation for our gamma matrices, and so we picked one that people most of the time work in. It's called the Weil, or I think I called it the chiral representation. All right, and that's where you write everything in block diagonal form. So for example, gamma 0 looks like this, and then the gamma i's can all be written in terms of the Pauli matrices. All right, something like that. And then you can even go further and write these guys in shorthand notation like this, where the matrix gamma mu is written as 0 and sigma mu, sigma bar mu, 0. And these, and so these sigma mu's are, so sigma mu is a 4. It's like, it looks like a 4 vector, but it's really, a 2x2 matrix made up of 1, and then the sigma vector, and sigma bar mu is 1 minus 6. And so this shorthand notation allows you to make a lot of computations a lot simpler than they are if you didn't use this notation. Okay, and then we said, okay, all right, well, using these matrices, we plugged that into the Dirac equation, and I wanted to see what the Dirac equation looks like in terms of matrices. And plugging those gamma matrices in, we were able to get a matrix equation that looked like this: minus M P0 minus sigma dot P. P0 plus sigma dot P times minus M. And then this is hitting this would be our psi, our 4-component Dirac spinner. But since we've broken everything into block diagonal form, we break psi into two component spinners. And for reasons that we didn't make explicit in the beginning, we call them psi L and psi R, and this all has to be equal to 0. And so if you multiply this out, it gives you two equations. So you get P0 minus sigma P psi R equals M psi left, and then P0 plus sigma P psi left equals M psi R. All right, so what you see is that the Dirac equation predicts the existence basically of two types of particles, and we don't really know how they differ yet, but it's two different particles, right? And in this case, they're coupled. These equations that describe the motion or the dynamics of this field are coupled to the dynamics of this field through these mass terms. And this kind of plays in with what Dr. Nygren was talking about last week, right? Because if you take the massless limit, then these guys go to 0, and these equations decouple. All right? So it's the mass term that causes these particles to kind of oscillate back and forth into each other. Okay? And that's what. So that's why these Weyl equations are good equations to use to describe neutrinos. Right? And we said that the reason these things are called psi L and psi R, L stands for left, and R stands for right, and it's just a convention, but it's how they transform under what we call the chiral operator, what we call it, the chirality operator, right? And it is called gamma phi. And it's defined as the product of all of our gamma matrices, right? Or in matrix form, -1, 0, 0, 1. All right, so you can see that if I operate gamma 5 on a purely left-handed state, so it has no right-handed component, I'm going to get minus psi left. And if I operate on a purely right-handed state, I get a plus. Okay. So these guys are eigenstates of this chiral operator, and that's how they transform. So this transforms like a right-hand particle, this guy like a left-hand, so that's why we use the subscripts left and right. We also saw that these guys are eigenstates of another operator, which you can get from the equations I'm just now erasing. But you can show that they're eigenstates of what's called the helicity operator. So this operator operating on psi right gives me psi right, and this operator operating on psi left gives me minus psi left. So they transform, or their eigenvalues are identical to the case of chirality. The only problem with helicity is that it's a frame-dependent quantity. Right? Because it depends on the momenta, you can always boost into a different frame where a left-handed particle would look like a right-handed particle, and vice versa. Okay? For massive particles. For massless particles, chirality and helicity are basically the same thing. Okay? And then we went through and we showed that negative energy particles, or what we call antiparticles, behave oppositely to this. So in other words, under these helicity operators, psi right goes to minus psi right, and psi left goes to plus psi left. Okay, so that's where we were last time when we left off. And what I want to do today is I want to, at least in a hand-waving kind of way, prove the Lorentz invariance of the Dirac equation, and in the process, it'll lead us to how to write down the Dirac Lagrangian, and then I want to start exploring the free particle solutions of the Dirac equation. Okay. So the first thing I want to do is Lorentz invariance. All right. So to start, to investigate Lorentz invariance, we need to know how the fields psi and how the gamma matrices transform under these Lorentz transformations. So under a Lorentz transformation, how do these guys transform? All right. Well, we've already worked out this case. In this case, the field just transforms much like a vector field, or a scalar field, right? It's just some Lorentz transformation matrix operating on the field. Okay, and we spent some time talking about that the fact that this thing is acting on a 4-component spinner, so it's really like a matrix made up of some factors of the Lorentz transformation matrix. And we talked about the infinitesimal form of this guy, and we wrote down something like this: minus I omega rho sigma S rho sigma. Or these S's are the generators of Lorentz transformation in this spin 1/2 representation. Okay? And remember, these guys obeyed a certain commutation relation that it needed to satisfy in order to be a good generator for a Lorentz transformation. Okay? All right. So what we're after is so we know how the fields transform. They just transform under these spin 1/2 representation Lorentz transformation matrices. Say that quickly 5 times. But now we want to try to figure out how these gamma matrices transform. Okay, so they look like, you almost think that they would just transform like a 4-vector, right? We know that 4 vectors, like let's say V mu, if we were to do a Lorentz transformation on this guy, it would just be mu, V nu, right? That's when this guy is a normal 4-vector. In other words, it has a V0 and a vector, 3-vector piece, right? But this gamma, this is a matrix, right? It looks like a 4-vector, but it's not really a 4-vector, okay? It's made up of matrices. But let's see if we can figure out how this thing transforms under a Lorentz transformation. All right? Okay, because remember what we're doing is we're trying to show that this thing the Dirac equation is Lorentz invariant. So in other words, if we perform a Lorentz transformation, if we boost or do some rotation, we better get the same equation back out. Okay? And so that means that we need to know how the field transforms. We know how this 4 derivative transforms. It transforms just like a 4-vector. We need to work out how the gamma matrix transforms. And so I'm going to start with what Peskin says. Peskin says that through a short computation that I'll leave for your own enjoyment, that you can show that this guy has a commutation relation with the generators of these Lorentz transformations. And this commutator takes the form of, I can't remember how I wrote it class, but these are the boosts. Remember I think there's a homework problem with these guys, right? These are the generators of the normal 4-vector Lorentz transformation, right? Times gamma day. Okay. So through a short computation, you can show that. All right. So what does that buy me? Well, equivalently, what I can do is I can multiply out the left hand and right hand sides. I can add and subtract ones. I can multiply by a small parameter, this omega thing. And I could show that this guy implies that I can have 1 plus I over 2 omega rho sigma S rho sigma times gamma mu, and then 1 minus I over 2 omega rho sigma. Again, this is, like I said, just adding and subtracting ones and multiply through this with this thing. Okay? So it's another short computation. And you get something that looks like this. Okay. But what is this thing? Well, remember, these are infinitesimal transformations, right? These are the transformations in the spin 1/2 representation. This is the infinitesimal transformation in just the normal, for a normal 4-vector. All right, so what it's telling us is that if we perform a Lorentz transformation on gamma mu in this spin 1/2 representation, so if we do this type of transformation, these guys do in fact transform like 4 vectors. Okay. Under a Lorentz transformation in our spin 1/2 representation, which is what we're working in with the Dirac equation, this guy, Okay, so under this type of transformation, the Dirac gamma matrices transform just like a 4-vector would. Okay. And again, just to reiterate, this gamma 1/2 here is a finite transformation, so it's the exponentiation of this. So we compound a bunch of infinitesimal ones, and it's minus I over 2. Okay, so I'm outlining the idea here. Okay, so we're after how does the Dirac equation transform? We have to figure out how psi and gamma mu transform. Psi, we know how it transforms. We talked about that a couple weeks ago, right, through these generators. And then we want to ask ourselves, how does this thing relate to these generators, right? So one way we can investigate that is to compute the commutator, and we find that this commutator gives us a gamma matrix back out with the generators from normal boosts and rotation type of generators. Okay. From there, we can do some more algebra, get a relationship that looks like this, which if we compound a bunch of transformations, we find that gamma matrices under this Lorentz transformation in the spin 1/2 representation transforms just like a 4-vector. Okay? All right, so now we have how these guys transform, and we know how the field transforms. Now we're ready, able to compute the Lorentz transformation of this guy, a general Lorentz transformation. Okay. So let me start. All right, so let me start by rewriting the equation. So I have I gamma mu del mu minus m, and it's all operations. Right? And keep in mind that this thing is 0. Okay. So let me do my Lorentz transformation. So I need to transform my 2 objects here, which are the 4-vector and the field. So this is a covariant vector, so it goes like lambda minus 1 verse. This is mu. Mass is just a scalar. The psi transforms as lambda psi. And it's spatial space-time argument gets transformed by minus. Okay. All right. Okay, so just keep in mind, I'm gonna drop this argument, but just keep in mind that that's what it is. Okay, so I need to somehow make this look like this. Okay, and the way I'm going to start is by Michael. What do we do?
You say what?
Multiply by 1. Exactly. All right. So I'm going to multiply by 1 out in front here in the form of lambda 1/2, lambda inverse 1/2. So this thing's just 1. Right? And I still have all this stuff here. Minus 1/2 sine. Okay, I'm just, again, remember, I'm just suppressing this argument. Okay? All right. So the next thing I can do is I can take this guy and push it through, and take this guy and push it through. All right? So this guy is going to commute with this, right? Because it's just a function of that. Right? So what I can do is push this lambda to minus 1, and as far as it's only going to go until it hits this guy. Okay? So I have I lambda 1/2 minus 1 down mu, and then this guy can go all the way through. So I have lambda 1/2 here. And then what do I have? I still have the lambda minus 1 mu down mu. And then lambda 1/2, when it meets lambda 1/2 minus at this m, it's going to just give me 1. So I just have m here. And I have psi. Okay. But this guy, I already just erased it. But this guy is what we just computed, right? That's the transformation of the gamma matrix in this spin 1/2 representation. And it's just lambda, mu sigma gamma sigma. Okay, so that's what that thing reduces to. But when I multiply this by that, it's going to give me a what? Anybody know? It's going to give me a delta function, right? Kronecker delta function, because I'm contracting mu's here. And so it's going to give me a Kronecker delta and the nu and the sigma. Right, so 0 equals lambda 1/2 I, what do I have left? Okay, gamma sigma, and then I said a Kronecker delta and sigma nu, and del nu minus m psi. With this Kronecker delta can hit this gamma, and just leave me with I gamma nu del nu minus m psi. All right, so what I have is the original form of the Dirac equation. Okay? And so that means that this right-hand side also equals 0. Okay? So the Dirac equation, we've written it down in one frame, and then we do a Lorentz transformation to another frame, and we end up finding that it still gives us the resultant is still 0.
The delta 1/2 just is the transformation.
Yeah.
Or lambda.
Well, yeah, the lambda 1/2 is, yeah. But the important point is that, you get back the Dirac equation here.
Could you please explain again why this delta 1/2 contributes to
Well, it goes back to that argument when we talked about in general representations, that if this is our Lorentz transformation, then the Lorentz transformation in any other representation is going to be some function of this guy. All right? And this thing will always commute with that.
We haven't shown the explicit form of this. We don't know.
Well, we do. We know it's written. Yeah, we have. It's written in terms of those S matrices, as we knew, and those guys go like. Trying to think. In block diagonal form, they go like six. They go like poly matrices, something like this. I don't have enough indices here. So this would be like. I have it somewhere. Yeah. So like, well, I have the ones for the boosts. They look like this. All right, but they're written in terms of spinners. I mean, polymatrices, and rotation. Yeah, I don't remember. I have to go back and look at how we define S mu, but we do have explicit forms of these guys. So you can convince yourself that it will commute with that. All right. Okay, good. So the Dirac equation is Lorentz-Marian. All right. So that's a good thing. So we can move on and try to derive. We know that in quantum field theory, we always want to work with Lagrangian because it's explicitly Lorentz scalar. All right, but first I want to show you a cute little thing that you might have heard me mention, or you might have heard mentioned somewhere else, and that's that. Where am I? Yeah. You might hear people say that the Dirac equation implies the Klein-Gordon equation. You might hear this, or you might hear people say that the Dirac equation is more fundamental. Or no, I don't want to say that. Let's say the Dirac equation contains more information than Klein-Gordon equation. Right, because we've already seen that this psi satisfies the Klein-Gordon equation, right? But what I want to do is show you where these statements come from. And to see, all you have to do is hit this guy from the left by it's basically a complex conjugate of this. So if I hit this with minus I, let's call them gamma nu, del nu, just to be general. And here I have I, gamma nu, del nu. Yeah. Okay, let me multiply this out. So here I have gamma nu, del nu. Here I have plus IM, gamma nu, del nu. Here I have minus I, M, gamma mu, del nu. And then finally plus M squared. All right, and this is all still acting on side. Okay, so these cross terms, these two guys, cancel each other out, right? Because the nu here is contracted and mu here is contracted. Okay, so the cross terms cancel. Okay. And now I can use another trick because these guys are being contracted on these two here, right? So I can actually symmetrize this first term. So In other words, I can write gamma mu, gamma nu, del mu as 1/2 gamma mu, gamma nu, plus gamma nu, gamma mu, del mu. Right? And I'm not using any fundamental, identity of the gamma matrices here. I'm just using the fact that these are being contracted on here. So I'm free to call them whatever I want. So here I'm writing these guys as gamma mu, gamma nu, right? But I could imagine, since these are being contracted, I could call this guy gamma nu and this mu, this nu and this mu. Right? It's the same thing because they're all being contracted out. Right? And so this guy is nothing but the anti-commutator. Del mu, del mu. Right? And the anti-commutator of the gamma matrices is 2G mu nu. Right? So if I get the 2 that cancels this guy, I get a G mu, mu nu, del mu, del mu. Right? And that is just del squared. Right? So when I go back and I look, this term, this gives me del squared. Right? And the other piece that I have left is the n squared piece. And that's nothing but the Klein-Gordon equation. Okay, so why do you want to, we already worked through solutions for the Klein-Gordon equation. Why don't we just, apply those to the Dirac case, right, the spinor case? And the answer is that this guy is for a scalar, right? So this guy, when you apply it to this spinor, it's basically washing out all the information that you have about the spin. Okay? Spin is still here, right? Information about the spin is still here. Okay, so that's why you want to work with the Dirac equation when you're talking about spinors. Okay. Even though it's, they're basically, the size satisfies both of these equations, this guy contains more info, right? Because you can extract information about spin and so on and so forth. Okay. Let's make sure this was it.
And in the Dirac equation, also m is a scalar.
Right.
So since in Klein-Gordon equation, since m squared is a scalar, we don't have the information about this. And there is also a scalar.
No, I think the loss of information about the spin is coming from the fact that you're losing this guy. And remember, this guy contains, it depends explicitly on the Pauli matrices, right? And that's where spin information is going to come from.
Yeah, and only in this representation do the Dirac matrices make the metric tensor, right?
Mm-hmm.
So we chose it to be like that, right?
No. These guys satisfy this no matter what representation you work in. Yeah. This you can show by going back to how we wrote these in terms of the alphas and betas. Yeah.
So there's nothing that the Klein-Gordon equation has and the Dirac equation that doesn't have.
So there's not. Let me think. I said there's.
Is there any more information in the Klein-Gordon equation?
No.
No.
Yeah. No. I mean, this just tells you basically that this guy. We're going to use this in just a minute. That this guy obeys like a wave-like equation, right? It's a plane wave. Okay. But that's basically all that's here. All right. Okay. So we've seen that the Dirac equation is Lorentz invariant. We've seen that now that the Dirac equation implies the Klein-Gordon equation, so the Dirac field obeys both of those equations. And we'll use that, like I said, in just a minute, to try to figure out the form of the solution for this equation. But first I want to just talk about how do we write down a Lagrangian, right? We still need a Lagrangian to work with. And so if we want a Lagrangian for our Dirac field, we obviously want the Dirac field to appear in that Lagrangian, right? But we know that we have to make scalars, right? This guy is a scalar under Lorentz transformation, right? So this is a Lorentz scalar. Right? So we have to figure out how do we construct scalars, Lorentz scalars from our fields. Right? And it's useful to keep in mind that this guy's like a column vector, right? And so that means that psi dagger, right, which is like a Hermitian transpose, would correspond to a row vector. I don't know. It helps me, keep that in mind. So if I want to build a scalar, my first guess would be to take psi dagger psi. Okay. So remember how we construct Lagrangians. We start with whatever symmetries we have. Here we have space-time symmetries, right? So we're enforcing Lorentz invariance of a Lagrangian, and we'll write down all terms that we can. We're going to write down non-interacting terms for the time being. Okay. So I'm looking for terms that I can construct that are scalars. Okay. All right. So what about this guy? All right. Well, what happens to this guy under a Lorentz transformation? Well, under a Lorentz transformation, this would become what? Psi dagger, and then lambda 1/2 dagger, lambda 1/2 psi. And what we need is for this guy to just be equal to psi dagger psi, right? And that's what would happen if we were talking about the regular Lorentz matrix, right? But in this case, if you go back and you look how we wrote these transformations in terms of those generators, these guys are not Hermitian, right? They're not Hermitian. What was I going to say? Oh, so what happens is that this guy does not equal psi dagger psi. It's something else. And you can see the fact that they're not Hermitian because of why? Because the generators aren't Hermitian, right? So if you look at SV nu, what I'm saying is, okay, these guys, so it's because these guys are not Hermitian that this thing isn't just one, right? Forget what I was saying about these guys being Hermitian. It's because these guys are not Hermitian. So if we wrote out these generators, so for example, look at the boost for this one, you can see that this is sigma I, 0, 0, sigma I. Okay, so the boosts are written like this, and you can easily see that if I take dagger of this, what's going to happen? All that's going to happen is I'm going to get a plus here, right? Because these guys are Hermitian, right? So we see that S0I dagger is equal to minus S0I. Right? So it's obviously not Hermitian. And that implies that these guys are going to cancel each other out. They're not unitary. That's the word I was looking for. Okay? So we need to figure out a way to fix this. Okay, so psi dagger psi is not going to work. Okay, but I can define a new quantity, And just do it. Let me just do it. Okay. So I'm going to define a new quantity. I'm going to call it psi bar. Okay. Psi bar, I'm going to define it as psi dagger times gamma 0. Okay. And then I'm going to claim that instead of psi dagger psi, psi bar psi is a Lorentz scalar. Okay. So let's see what happens. So under a Lorentz transformation, I still get psi dagger, I still get gamma 1/2 dagger, and I got my gamma 0 here now, and then I have gamma lambda 1/2 psi. Okay. So what I need to show is that this thing is equal to psi bar psi, right, for it to be a Lorentz scalar. Okay.
Do you want to interpret them as the probability of what we have in quantum?
Do I want to?
You want to interpret this psi bar psi as a probability of finding?
No, not necessarily. No. Yeah, because remember these aren't wave functions anymore, right? These are field operators. Okay. Yeah, so it's not necessarily it's not related to probability. All right. But what I'm looking for is to be able to write down a Lorentz scalar. Okay. So the first thing I do is I look at this guy. Okay. And so let me look at it in the infinitesimal form because it's a little easier. So that guy would look like psi dagger, and go square here, 1 plus I over 2 omega mu nu plus mu nu. This thing's daggered, right? And gamma 0. Okay? So you go back and you look, okay? So there's 6 of these guys, right? There's 6. There's 3 rotations and 3 boosts. All right, so let's see what happens when we consider these cases, one at a time. All right. So the first case I'll consider is the rotation terms. Okay, so the rotation terms are where this is Sij. Right? So mu or nu, neither one of them equals 0. And for that case, these guys, Sij dagger, these pieces are Hermitian, so this gives me Sij. And these guys, you can show, when you plug in, will commute with this guy. Okay? So that means that for the rotations here, where the I and J would be here, this dagger just gives me back Sij, and then I can take gamma 0 back through there. Okay? For the other case, where I have boosts, as say S0I dagger, we just showed that this is minus. Right? But this guy, gamma 0, anti-commutes with these. Right? So it basically cancels off this plus sign. So here we're using the fact that for the rotations, they're Hermitian plus the commutator of Sij gamma 0 is 0. Here we're using the fact that this thing is anti-Hermitian and that S0I gamma 0, what did I say? It gives me what? No, the anti-Hermitian. gives me a minus sign. Okay, so using those, the plus here is not literal, kind of, all right. Just in addition to those facts, okay? And so what it means is that when I pass this gamma 0 through here, it stays the same, right? I get back, what am I trying to say? So basically, passing gamma 0 through here is going to just remove this dagger, right? And that's what we want, right? Because this will become now, so if I pass gamma 0 through here, I have psi dagger, gamma 0, 1 plus I over 2, S. Right? And this thing is lambda 1/2 to the minus 1. Right? It's just the inverse. And so that means that I can pass this guy through here. So let me just change this to lambda 1/2 minus 1. And here I have the lambda 1/2 psi. Right? So these guys, this is just the inverse, so they cancel each other out. And I end up back with psi bar psi. Okay? So this guy is a good candidate for a Lorentz scalar. Turns out that there's another quantity that we can use, and I'm just going to write it down and then probably make it a homework problem. But it turns out that you can construct psi bar gamma mu psi, and this thing is a good Lorentz vector. Meaning that I can dot that into another 4 vector and get a scalar. Okay? So in the end, I can write down Dirac-Lagrangian that when I apply the Euler-Lagrange equation to motion, give me the Dirac equation. And that equation is psi bar I del slash minus m psi. Okay, so this is the Lagrangian for a non-interacting Dirac field. And leave it as it'll be homework to apply the Euler-Lagrange equation to motion to this and get the Dirac equation. It's like a 2-liner, so it's not that hard. Okay. All right, so any questions there? Okay, so let's start talking about the solutions to the Dirac equation. Okay. All right, so let's think about this. So we have our field psi, right? And we know it obeys the Dirac equation, but we also know that it obeys the Klein-Gordon equation, right? And the Klein-Gordon equation, the solutions to that are just plane waves, right? So this thing we could write as some linear superposition of plane waves. Right, something like this. It's going to be a plane wave, and these guys are 4 vectors, okay? But remember, this thing, like I said, is a column. It's a column vector, right? So what we need to do is put in a column vector. And so I'm going to put in just kind of a general column vector, call it U. Okay? So just to remind you, the P here is the 4 vector, so P squared equals M squared. All right, and for the time being, we're going to focus on the positive frequency solutions, or the positive energy solutions. In other words, our P0 is greater than 0. Okay. We'll come back to the negative energy solutions later. All right. So this equation satisfies the Dirac equation, satisfies the Klein-Gordon equation. Let's plug it into the Dirac equation and see what we get. Okay, so I'm going to take I gamma mu del mu minus m and operate on this guy. So I have u of p, e to the minus I p x. Right, so what's going to happen? So I have this 4 derivative here. It's going to hit this guy. Right, so it's going to bring down a factor of minus I p mu. Right, p sub mu. Right, and that's going to get dotted. So the minus I is going to kill this I out. Right, so I'm going to have gamma mu p mu minus m u p. And now, once I've acted with this derivative, I can just get rid of this plane wave solution, right? Because I've got 0 on the right-hand side. And so this is telling me that whatever this column vector is, it has to satisfy this equation. Okay? So this is the equation that we want to try to solve. And the easiest way to do this is not to just start in some general reference frame, but to start in the easiest reference frame there is, which is the rest frame. Okay? In the rest frame, P, the 4 vector P, is just what? It's just the mass. Okay? It's got no free momentum. Okay? And the reason you can do that is because once we solve it in the rest frame, then we can use our boost, our Lorentz transformations to boost to any frame that we want. Okay, we're using the Lorentz invariance of the Dirac equation. The fact that we can solve this in the rest frame and then boost any frame we want. Okay, so let me do that. Okay. So that means when I plug for the rest frame, so let's work in the rest frame. All right, so in the rest frame, this is what? Gamma 0 is the only non-zero piece, and P0 is just M. Right? And then I have minus M. Right? And don't forget that there's an identity matrix here. So I'll write it in kind of light, ghost of it. Matrix, and then U of P. Okay. And if I write this in matrix form, the factor of n, I can factor out. And here I get minus 1, 1, 1, minus 1. All operating on U, and actually P here is just P0. That's the only non-zero combined. And you can show that the spinner that satisfies this equation can be written as U 0. I'm going to try to do C's. Okay? And factor square root n. Okay, so these C's, 2 component, so try again. 2 component spinners. And we normalize things such that C dagger C is just 1. And this square root of m, you might ask yourself where this comes from. And this is what I call convenience factor. we put it in by hand because we know we're going to need it later on, or it's going to simplify our lives later on.
It's the same C. It's
Mhm.
not like C1, C2.
Same seed. And it just comes from this guy. Okay, so how do we interpret this C? Well, we can go back and look at our generators, branch transformations. In particular, we can look at the rotations. Remember the rotations, something like this. They have 1/2 epsilon I to the k, and they have these sigma k's. So what happens is if we do a rotation on this spinner, we see that these guys they transform, or they transform under the rotations of our ordinary two-component spinners. Right, so we can set up our coordinate system where these guys are our old friends, spin up and spin down. Right? In other words, we can write psi plus is 0, psi minus is equal to 0, 1. And the SZ basis, if you will. Okay? So the fact that when you look at the rotations and these guys are being operated on by the Pauli matrices, it's telling you that they transform under the SU2 transformations. So the spinner, our old friend, two-component spinner. Right? And it's this C, like I said, it's this C that determines spin orientation of the Dirac solution. Okay? So we can always set up our coordinate system however we want. If we point it, in the SZ direction, align it with the SZ direction, then we'll have one solution that's spin up, one solution that's spin down. I think I'm going to stop there because the next, so we have the solution. This is the solution. I'm sure I made a bigger deal out of it, but this is the solution in the rest frame. Okay, so we have the solution in the rest frame. The next thing we want to do is boost this into a more general frame, right? To see what the solutions look like, and that takes a few pages of work. So I'm going to stop there because I don't think I can finish it before the end. All right. Any questions on this stuff? No? Crystal clear. Like I said, I'll post these notes. There's some places where some steps are skipped, and that's on purpose because they make good homework problems. Homework problems that I have already have the solutions for. But if there's anything that's not clear, as always, just send me an email or come see me. Okay.
What's the relationship between S, I, J, and U again?
Sij and mu
and in U that we found.
Oh. It's just.
Why are we talking about S, I, J?
Well, we were trying to understand what these guys are.
Oh.
Right? We found that we took the rest frame limit and we found the solution is of this form. Okay, so we're at rest. Okay, and then we ask ourselves, how do these things transform, let's say, under rotations? And we look at the rotation generators and we see that they're made up of Pauli matrices. And so that's telling us that these guys are, spin 1/2, two-component spinners. Right?
Okay, so they have to So we're looking at the way they transform, the way that C transforms, and because of the form of S, they transform like spin matrices.
Yeah, like our SU2.
That's kind of a proof. For, this is kind of a proof for the Dirac equation that represents its 1.5 particle.
Proof.
Before this, we didn't know if this equation describes its 1.5 particle.
Yeah, I don't think it's a proof. I think that the fact that it represents spin 1/2 is built into it from the beginning. In the way that you define the alpha and beta matrices. Remember, we wrote those in terms of the Pauli matrices, and that to me is telling you that
Has something to do with the eventual explicitly that this is the case that this equation applies to the
Yeah, I think this shows it kind of more explicitly, but the fact that the Dirac equation,
it's not Huygens proof.
it's not a proof. No, like I said, that's built into the Dirac equation in the way that you write it down, right? And the way that we construct those matrices. Okay. All right. So I'll see you